I'll hand it over to you.
Okay, great.
All right. So, good morning, everyone. Thanks for joining the DataCon LA 2021. My name is Ho Chan San, your host. Our co-host today is Nancy and Lucy. We will be moderating the chat and Q&A for during this session. Today we have our guest, uh, Dr. Mark Jackson. He will be talking about the quantum computing, the next new technology in computing. Let me introduce him a little bit. Dr. Jackson, he is the quantum evangelist at Cambridge Quantum, and he received his PhD in superstring, right? Theory physics at Columbia University, and is joining us from Portland, Oregon. Without further ado, I'll be hand this over to the speaker, and thank you for being here, Mark.
Super. So thank you, Ho-chan, and thank you, Nancy, for hosting and moderating this. It's a pleasure to be speaking at DataCon LA once again. I'm sorry we can't all meet in person, but I am joining you from Portland, Oregon, and I hope in the future we will be able to all meet in person. So let me go ahead and share my screen now, and you should see that. And so I think you should be able to see my presentation. Is that correct, Ho-chan?
Yeah, I can see it now.
Good. So today I'll be telling you about quantum computing, the next new technology in computing, and I am the quantum evangelist at Cambridge Quantum. First, I just want to say a few words about our company. So we're a company about 7 years old. We focus exclusively on quantum computing, in particular software. We're focused on developing quantum applications in the near term. So we're not interested in things that would only be useful 20 years from now. We want to do things right now. We have about 150 people, mainly in the UK, but a few of us in the US and a few in Tokyo. We focus on compilers, chemistry, machine learning, and cybersecurity, and I'll be talking about all of those very quickly in this presentation. And the big news is that we are in the process of merging with Honeywell's quantum group. And so very shortly, we will form a new company, which will be the world's first comprehensive quantum computing company with expertise both in hardware and software. And we will be the largest quantum computing company with almost 400 people. So I think I'd like to begin by introducing what's usually considered to be the first computer. So this was by Charles Babbage, coincidentally in Cambridge, about 200 years ago. And even though it looks comically antiquated by today's standards, it actually has all the ingredients that we would identify in a computer today. It has input devices and output devices, and in particular, the way that it processes and stores information is identical because it stores it in switches, and these switches are either on or off. And so by cleverly manipulating these switches, you can do useful things. And in 200 years, we've done a lot in computer science. And this is a picture of the laptop that I'm using to give this presentation on. It's obviously much faster and much easier to use and more sophisticated, but conceptually it's identical in that it still uses on and off switches. We just call them transistors, and they're smaller and faster, but they're still the same thing. What I'll be telling you about today is the first leap in how we process information in 200 years, and it's quantum computing. And the reason that it's so different is because it doesn't use bits. It uses quantum bits or qubits. And a qubit can be a mixture of 0 and 1. So the technical name for this is superposition. And so there's some amount of zero-ness and some amount of one-ness. But it really is both at the same time. And when you combine that with another physics concept called entanglement, you can unlock a vast number of states. And I'll explain why that's so important here. So in the upper left-hand corner, this is my favorite molecule, caffeine, and it has 24 atoms. And we know what the equations are to simulate molecules, and so that's not a problem at all. But if you tried to build a computer to simulate caffeine exactly, you would have to build a pretty big computer. It would be 1 to 10% the size of the Earth. So that's possible in principle, it's just not very practical. Penicillin, on the other hand, is a bit of a larger molecule, and you would need a computer the size of the entire universe. So that's actually the theoretical limit. We obviously can't build anything bigger than that. So this shows the limit of normal computing in trying to do some of these types of calculations. Quantum computers, on the other hand, can do this with a pretty modest amount of qubits, with only about 160 or 286 qubits. And so that's why we're so excited about quantum computing. It's not just that it's a faster computer, it is so much more powerful, it could be used to solve problems that we never could have hoped to have solved before. So this is a map of all the different things that are connected to quantum computing. And again, it's not just one advance, it's several advancements all related in quantum machine learning and chemistry and simulation and communication and algorithms. So this will really impact all areas of science and technology. I'd love to talk about this, but it would take a long, long time. And so I'm just going to focus on a few developments in this presentation. So what does a quantum computer actually look like? So these are two examples. On the left, this is IBM's machine, and it uses an approach called superconducting. And you notice it kind of looks like this chandelier, and that's because it's usually lowered into a giant refrigerator, a cryogenic chamber near absolute zero. And on the right-hand side, this is a quantum computer built by Honeywell, and it uses a different technology called ion trap, and they use lasers to trap charged particles called ions. And so these are two major examples of quantum computers. We know of over 100 different quantum computers just in the Western Hemisphere alone. So I really want to communicate that they really do exist. This is not just science fiction buzzwords. Quantum computers really do exist, and many groups are using them. So I've mentioned the superconducting and ion trap approach. There's also photonic, as well as several others. And many different major corporations, such as Google and IBM and Honeywell, are getting into the game. There are several startups like Rigetti and IonQ, and many academic groups are also doing this. There was a major announcement about 2 years ago by Google called quantum supremacy. And this means that Google found an example of a problem that a quantum computer could do that a normal computer could not do very easily, at least. And this was published in academic journals and peer-reviewed, and so this really has been accepted. There's a lot of progress to be made, but this was a major milestone. It showed that quantum computers could solve things that normal computers couldn't do. So again, this was almost 2 years ago. When we talk about the power of quantum computers, it's not just the number of qubits that's important. It's also the quality of the qubits, their error rate and the coherence time and things like that. And so IBM has popularized this term called the quantum volume, which is one metric which includes all of these factors and which is an estimate of the quantum computer power. So it allows comparison among different quantum computers. And to show the progress that's been made in the past few years, so the blue line here shows the progress made by IBM, and they've been able to double the quantum volume at least every 12 months, if not sooner. And for comparison, Moore's law, which I think many of you are familiar with, has shown a doubling in classical computing power every 18 months. So just the blue line alone is quite a bit faster than Moore's law. The orange line shows the progress made by Honeywell, and it's on a much faster trajectory. Honeywell has been able to increase the quantum volume by a factor of 10 every year for the past several years, and they believe that they can increase at this rate for the next several years. So we see that in the next few years, we expect a great increase in the power of quantum computing. IBM and Google have both predicted they will have 1,000 qubits within 3 years and 1,000,000 qubits within 10 years. So a lot of resources are being put into this. This is a quantum program. This is how different it is from a normal quantum computer. Whatever the quantum algorithm is, it follows these three major components. So on the left, there are quantum bits. So you read this from left to right. Each horizontal line there is a different qubit. So there's the initialization on the left-hand side, and then different operations are applied to the different qubits. And then at the end, there's the measurement. So until the measurement, these qubits exist in this superposition and entanglement state. And it's only at the very end, when you measure the qubits, you force them to choose, are you a 0 or are you a 1? So the output is purely classical. The output is just several bits. But in between the initialization and the measurement, all sorts of quantum processes happen, and you don't get to peek into this. You just have to apply these operations, and then only at the very end does it do the measurement? There's this very sophisticated technique called quantum error correction, and that's because these qubits are very fragile creatures and very easily can give the wrong answer or spoil their quantum properties. And so classical error correction is very easy to do, but quantum error correction is much more subtle. And we're only now getting to the point where we can do this quantum error correction. About a month ago, Honeywell and Google both published articles showing that they can now do this quantum error correction in real time. And so there's going to be a great jump in the sophistication in programs that we can run once this quantum error correction becomes mainstream. Right now, we don't have this quantum error correction, and we don't really have the quantum computers of our dreams yet. We have what's called NISC era machines, noisy intermediate scale quantum. And that means that we have about 100-ish qubits at most. They still have a relatively high error rate. We can't really do the error correction because error correction means that you're spreading the information over several qubits, and we don't have that many qubits to spare. So we have been focusing on what are called hybrid algorithms. The program has instructions sent to both the quantum computer and the classical computer. Most of the heavy lifting is done by the classical machine because those are still much more powerful than the quantum machines. And then there's this feedback between the quantum and the classical computers. What can we do with them? So why are we going to all this trouble of building quantum computers? So I mentioned the example of chemistry, and that's very useful for pharmaceutical companies to design drugs, as well as in material science companies, like designing better batteries, for example. In the industrial goods sector, there's logistics, like supply chain optimization and traffic and such. Machine learning is used all over the place, machine learning and AI, and doing things like that. And then finally, in finance, there's all sorts of trading algorithms which are used, as well as cybersecurity advances. And so I'd like to briefly talk about some of these aspects. In machine learning, this is an example, kind of a schematic of what a quantum machine learning algorithm looks like. And so on the left-hand side, of course, you see these horizontal lines. You prepare this quantum data set. So you transfer the data from classical into quantum, and then you apply operations to evaluate the quantum model. Then you do the measurements, and then that information, which is binary, is fed into your classical model, and then this evaluates the gradients and updates the parameters based on this output. And so there's this feedback loop. Again, you saw this in the hybrid schematic. And then finally, at the very end, you have some sort of optimized parameter. And so whatever machine learning algorithm you're doing, it follows this general schematic. There are several quantum machine learning algorithms developed, and these are some of the names here. On the right-hand column, you see the speedup, and some of them have a square root n, and some of them have a logarithmic n. So this shows the power of the quantum algorithm. So compared to a classical algorithm, which has order n, so if you double the data, or double the scope of the problem, you usually double the running time of the problem. But you see that the quantum algorithms are often faster. So square root of n means that you only need square root number of operations, and log of n means that it's exponentially faster than its classical counterpart. And so we know of several examples of each of them. So one example is an optimization where you're trying to optimize some parameter, like find the minimum or maximum, subject to some constraints. And fortunately, a lot of quantum optimization problems are exponentially faster than the normal machine learning, normal optimization type problems. An example of this is in radiotherapy, where you're trying to optimize the effectiveness of some tools subject to constraints that, doing the radiation is expensive and it could harm the person. And so you only want to use enough radiotherapy to help the person, but not harm it. And this is an example being used by Microsoft and Case Western Reserve. And so this is an example of an optimization problem which is being used right now. Another problem is the knapsack problem, where you have some sort of finite capacity, like a knapsack, and you can put objects into that, and each of these objects has a different value. So you're trying to maximize the value of what you can carry subject to this constraint that you can only carry so much. And this is a very typical problem in job scheduling and optimization. And our team has developed a quantum version of this, which we believe has a speed up compared to classical counterparts. This is an actual graph showing the output from the quantum computer. So on the left is the 5-qubit version, And on the horizontal axis, you see all the different possible permutations of whether you have each item or not. And then on the vertical axis, you see the probability, because we run the simulation about 1,000 times, so we get this histogram. And you see that the correct solution pops up about 72% of the time. So this was a small example, so we know what the correct solution is. And this is very typical of quantum programs, that you will probably get the correct solution, but you are not guaranteed to get the correct solution. And that's why it's important to run it several times. The trade-off is that you get this much faster. And then on the right-hand side, this is the 10-qubit version that we ran on a simulator. And again, you get the correct solution most of the time, but not all of the time. And it's the skill in developing quantum algorithms to try to maximize how often you get this correct solution. I'd also like to mention the quantum version of natural language processing. I think many of you are probably familiar with this from things like Alexa and Siri and such, in which they learn how to speak like humans, and they learn what we understand when we normally converse. There's a mathematical structure about natural language processing, and so it allows the computer to parse all these different words and figure out what we mean. There has been a lot of progress in quantum natural language processing, in particular this group by Bob Cook at Oxford, when his team realized that the mathematical structure behind language very naturally translates into quantum computing. And so we've been doing a lot of work. Bob Cook's team actually works for Cambridge Quantum now. And so we've been running experiments trying to develop more sophisticated versions of natural language processing. I'd like to spend a few minutes talking about compilers, which I think many of you are probably familiar with. Compilers are just translators between what we type in programming, like Python or C, into what the machine understands, because of course the machine only understands on and off switches to tell it what to do. And a good compiler doesn't just do this translation, it does it as efficiently as possible, because you want your programs to run as fast as possible and use as little memory as possible. And it's exactly the same with quantum compilers, and we have developed our own quantum compiler called Tiket. So Tiket translates any of the popular quantum programming languages like Qiskit or Q# or Cirq, and it allows you to execute these on any of the popular programming, any of the popular quantum hardware platforms like Google or IBM or Honeywell or what have you. And each of these platforms is very different, and I'll explain more in a second. You don't need to know any of the details of the quantum hardware platform. All the details are known to Tiket, and it will do this translation for you. And it's very easy to move from one platform to the other. You simply change one line in your code, and you can move your program from one platform to the other. So this is how it does it. You type your quantum algorithm in, and Tiket will first look at just the circuit, your quantum program, and it finds ways to simplify that. So it looks for patterns in these gates, and it looks for ways to keep the mathematical structure of the circuit, but find a way to express it using fewer gates. Then it finds a way to execute this circuit on the machine that you've chosen, and it has all sorts of subroutines allowing this type of optimization. So here's an example of something that you might do. So on the right is the IBM Melbourne quantum computer, and you'll notice that it has at most 4 qubits coupled to each other. So at most 1 qubit is talking to 3 others. And on the left, this is a typical quantum circuit, and you'll notice that there are some 5 qubit couplings. So the qubits on the bottom here, they not only talk to each other, but they are also coupled to the upper 3. And so naively, we might think there's no way to run this program on the left on the machine on the right. But that's not true. There actually is a way, and you can do this with something called routing. And so Tiket has all these sophisticated routing operations to find an efficient way to do this. Now, about 6 months ago, we made Tiket available for free without any licensing restrictions. So you're welcome to download it from this GitHub repo. I've given the URL there at the bottom. And so there's lots of examples and notebooks and such. And so you're welcome to use this right now for free. And if you develop $1 million app, then that's fantastic. We simply ask for feedback, and that you give us you give us acknowledgments if you end up writing an academic article using Tiket. I'm also happy to say that in a few weeks we will be making Tiket completely open source, and so that means that every aspect of Tiket will be available. So if you have a hardware group that you'd like to extend Tiket to support your hardware, you can build your own extension. And if you have an idea for a clever subroutine to do more optimization, you're welcome to add that feature. The final thing that I want to talk about is encryption and cybersecurity. And I think many of you are probably familiar with the basics of how encryption works. When you send information over the internet, you're usually not sending the information itself because it might be sensitive, like your credit card numbers, and you don't want someone eavesdropping and taking that. And so what happens is that we apply a complicated mathematical formula to your data, like your credit card numbers, and so the data gets mixed up, and that's what's transmitted, and then the person on the other end can undo that encryption formula using something called a key. And normally, encryption works pretty well. When you hear about hacking, it's usually because of a human error, like someone was bribed or they wrote their password down on a sticky pad or something. It's usually not because the encryption formula was directly undone. Unfortunately, quantum computers are quite good at undoing a lot of the popular types of encryption. So an example would be RSA, which is based on the difficulty of factoring large numbers. Normal computers would take millions of years to directly undo this, but quantum computers could undo this pretty efficiently. Maybe not today, but in a few years when they're a bit more powerful. And so this has a lot of cybersecurity experts a bit worried. Fortunately, they've been developing new versions of quantum encryption. So on the upper part of the screen, these are examples of encryption formulas that are being used today. And this represents about 99% of encryption, and they are all vulnerable to quantum computing. On the bottom half of the screen, these are the finalists introduced by NIST. And in the next few years, we expect about 1 or 2 winners to be announced. And all these formulas are based on mathematics that we don't think quantum computers are good at hacking. We're not sure. This is why the investigation is being done right now. So again, the good news is that we're already developing these. The bad news is that upgrading takes time. It's not just a matter of a few minutes installing it on your local machine. If you work for a government agency or you work for a big corporation, you probably know that upgrading can take a lot of time because of all these legacy systems. And so that's why I would encourage you, if you're in a position of power to do this sort of thing, to start upgrading right now. Don't wait until it's too late and you start reading headlines about quantum computers doing this type of hacking. Even though quantum computers can be used for hacking, they can also be used to protect communication. And there's a new type of communication called quantum key distribution in which quantum data is being sent. And it is completely secure because quantum data has this superposition and entanglement. And so based on this, any sort of eavesdropping or tampering can be detected. And that makes this fundamentally eavesdrop proof and unhackable. So to explain a little bit more about how this works, imagine you have a source of entangled particles. And so again, entanglement means you have these 2 qubits. They're in a random state, so you don't know what state they're in, but whatever state they're in the same state, so they're random together. So now measure this. So you have 2 measurement devices. We'll call them Alice and Bob. So Alice measures the first qubit in some direction, and Bob measures the second qubit in some direction. And they do this randomly. They don't compare notes until the very end. So only at the very end do Alice and Bob compare what they've done here. And if they've measured in the same direction, they should always get the same result. And that's because of the entanglement. And so now Alice and Bob share this secret key that's known only to them. Now let's redo that using some sort of eavesdropper. So the eavesdropper is grabbing one of the qubits and measuring it and then replacing it with what they measure. So if this were classical physics, this would be the perfect crime because there would be no way to detect that this eavesdropping has taken place. But this is a quantum system. And so Eve has broken the entanglement. And so even though she's replaced it, she can't redo the entanglement. And so now when Alice and Bob do their measurements, you see that even if they're measuring in the same direction, they don't always get the same result. So when Alice and Bob do their comparison at the end, a large fraction of the time, they will get different results. And so this is mathematical evidence that some sort of eavesdropping has taken place. So you don't just need to trust that communication is secure. There's actually a mathematical check of this. And so these type of quantum key distribution, or QKD networks, are already starting to be built. So you can do this over fiber optic, or even through empty space using lasers, like through satellites. So by way of summary, right now, we do have quantum computers, and we do have post-quantum encryption. I estimate that in about 3 years, we will start to see commercial applications. So groups will be using quantum computers for commercially viable things. And it is possible that we could start to see hacking from quantum computers. They'll be powerful enough to do that. I think within 8 years or so, quantum computers will be fully integrated in everything. They'll just be ubiquitous. You won't even know that you're using them a lot of the time. And I think that hacking would be likely from quantum computers. And so again, I urge you to make this upgrade if at all possible. So that was it for my prepared slides, but I'm happy to stick around and answer any questions that you might have. And here's my email address if you'd like to contact me later. So thank you. And again, I'm happy to answer any questions.
Could you put your email address back up? I was going to put it in the chat.
Sure. And thank you for putting the URL of tiket.
Thank you. Okay.
All right. We'll be waiting around 30 seconds for any additional email questions.
Okay, I have to paste. Where are you? Copy.
All right. It doesn't seem like there's any questions. That's fine. But feel free to email me if you'd like to get in touch. And thank you again, Ho-chan and Nancy, for hosting.
Thank you. Just alert the attendees. There's a feedback form in the chat. Please take the time to fill it out to help us make the conference even better next year, when hopefully we'll be seeing you live. Thank you so much, Mark.
Yes. All right. Thank you, everyone.
Bye-bye.
Thank you.
We're off now, I think, until 40. Okay.
We'll come back on 12:40. Yes.
All right. I'll see you then.
All right.
Thank you very much.
Thank you.